So now we want to do this problem on the mean value theorem. Okay. So like other things, if you Google mean value theorem, more information about the mean value theorem will come up than you ever wanted to know, probably. So you might want to do that if you're just absolutely clueless. But even if you are, A says state the mean value theorem. So what does the mean value theorem say? So I'm just going to regurgitate it from memory. This is what the mean value theorem says. You're thinking maybe, what else would you do, Hunter? Isn't that just remembering and using your brain? But you can kind of reason out what the statement of the theorem should be if you understand the picture. So here's the theorem in symbols. Maybe we'll do the theorem in pictures in a second. So it says, let a function f satisfy two conditions. So one condition is that the function f is continuous on the closed interval a, b, and it is, so the second thing here is that it is differentiable on AB, okay? And what do these two things mean? Being continuous just means that it's an unbroken line, right? And being differentiable means that it's smooth. It doesn't have sharp corners like that. And also, sometimes the derivative doesn't exist, right? Like that. If you think about the definition of a critical number, what is a critical number? It's a place where either the derivative doesn't exist or else it's zero. So this assumption 2 here rules out the case where the derivative doesn't exist, and so critical number and a root of f prime become the same thing. Accidentally drawing weird little triangles. So what's the conclusion? These are the assumptions. So if f is a function that satisfies these two conditions, then there is some input c in the interval ab such that, okay, now I'm going to write something that maybe looks kind of weird. F prime of c equals f of b minus f of a over b minus a. So a couple ways you can think of this weird thing. What is this? This is the average rate of change, right? It's kind of the average rate of change on the closed interval AB. If you'd rather think of it as a picture, you can associate everything with this picture. So let that be a x and y axis. So here's x, here's y. And maybe you have some a, and let's let b be over here. Alright, so maybe here is b, and the function takes that value at b. And now I draw some function to which the theorem should apply, so it's smooth. And what is it saying? It's saying something about some input c, right? It's saying that between a and b, some special c with some good properties exists. And what good properties is c supposed to have? It's supposed to have the good property that if you think about the secant line that connects a and b, then the tangent at c is exactly parallel to the secant line. And we went over how this is a generalization of Rolle's theorem from class. Okay, so it looks like this might be a pretty good C here. I'm just eyeballing it, obviously, but it looks to me like the tangent line at that point should be pretty much parallel to the purple line. So see what I mean? And that's where this average rate of change thing is also the slope of this purple line. And the algebraic description, this weird algebraic thing is just comes from labeling the sides of this triangle. Maybe I should get a different color. It's just rise over run, right? That's how you get the slope of the purple line. You can just check that the rise here is the difference in it's f of b minus f of a, and the run is just b minus a. So super fantastic. We have stated and reviewed the mean value theorem, so now we completely understand it. We have the flames of hell burning in the background, which always accompany the mean value theorem. And part B says, oh my god, look at how weird this question is. Does there exist a function f such that f of 0 is equal to minus 1 and f of 2 is equal to 4, and there's this weird condition on the derivative. So maybe we should just go right to a picture and... I mean, the answer is going to be that this somehow contradicts the mean value theorem. The answer is going to be no. But we have to think about why the answer is no. So let's kind of describe a function that could possibly be like this. So it says f of 0 is minus 1. So let's just say, here's minus 1. And it's saying that f of 2 is 4. So let's say this is 1 and here's 2. And it looks like maybe 4 should be about right there. So here it is. And now it's asking, right, okay. So notice that the statement never says anything about the function being continuous or differentiable explicitly, which makes you wonder, maybe we can cook up some f for which the mean value theorem doesn't apply. So maybe we can meet the condition on f from the problem and have some f which is immune from the mean value theorem because it's either not continuous or not differentiable. But you can't do that, and it's because of this assumption, this little and part here. So it says and f prime of 2 is less than or equal to 2. So I'm no lawyer, but to me that seems to suggest pretty clearly that the derivative is defined everywhere for this function. And remember, differentiable implies continuous. Differentiable. I find it really hard to talk and spell at the same time. I'm sure there is some neurological reason for that, at least in my brain. So if a function is differentiable at a point, okay, so you should think of this as just being smooth, then it is continuous. Because, if you look at the formal definition, this follows from a theorem, but also if you just think about what these things should mean, you can believe it, because differentiable means smooth, continuous means unbroken. So wouldn't it be silly if there was something that were smooth and broken? Right? If this weren't true, then there would be some differentiable non-continuous function, which doesn't make any sense to me. Okay. So this condition here about the derivative existing everywhere implies that the function is continuous everywhere. And so that means that that the mean value theorem is in play, because by assumption the mean value theorem is going to apply to this f. All right. So what does the mean value theorem have to do with anything? Remember, this is the height. It's supposed to be 4. Oh, shoot, I have my ruler tool on. Okay, so here's the height 4. And the mean value theorem has something to do with this line, right? So we have this condition here that says that the derivative can never be greater than 2, all right? But we also have the mean value theorem, and the mean value theorem says that no matter how we connect these... Sorry, my ruler tool is on. It says no matter how we connect these two things, as long as it's continuous and smooth, then there's going to be some point, C, where the tangent line is parallel to the blue line. Okay. So fine, all right. Let's call it, here's C. Stupid ruler tool, I hate it. So here's C. All right. So what is the contradiction? Well, we can actually figure out the slope of the blue line because we're given these values. So the slope of the blue line, the average rate of change on this interval from 0 to 2, that is just f of 2 minus f of 0 over 2 minus 0, which is 2. And they gave us all these. F of 0 is minus 1, f of 2 is 4. I can just figure out what this number is. Minus minus becomes a plus, and it's over 2. And so the slope of this blue line is 2.5. So why is that bad? Well, that's a little suspicious because the derivative is not allowed to be bigger than 2. But the mean value theorem says that there's some point where the derivative is the same as the slope of the blue line, which is absurd. It's a contradiction, okay? All right. These are supposed to be two arrows colliding with each other and the universe destroying itself because of the contradiction. Alright, so there is no such function because if there were, it would contradict the truth of the mean value theorem, and nothing is more true than the mean value theorem. So B is done. Alright, and so on the exam you need to say that kind of briefly in words. So what would be acceptable as an answer? Well, I would consider this an acceptable solution. You know, f of 2 minus f of 0 over 2 minus 0 equals 2.5. We saw that. But, but f prime of c is, say, less than or equal to 2, and this is a contradiction. So I gave you a long lecture with lots of pictures and colors, but this is a pretty good answer. Could be more explicit, right? You could say that what's being contradicted is the mean value theorem, but that's good enough. Good enough for me. I need to move this down. Oh my god. And now C is a completely different question. God, I hate these multi-part questions. It says, verify that the function satisfies the hypotheses of the mean value theorem on the interval 0, 2. So let's just do that first, okay? So f is this cubic polynomial, x cubed plus x minus 1. So we have to ask ourselves, is it continuous and is it differentiable? It's continuous because polynomials are continuous everywhere. It's differentiable because polynomials are differentiable everywhere. And you can write that down in English if you want. If you don't, I probably won't take anything off. But that's what this first sentence is asking you to do, is verify that the mean value theorem talks about functions like this one. So the second part says, and find all numbers C that satisfy the conclusions of the mean value theorem. So this is a rare exception to the universal rule for solving problems in Chapter 4, which is take the derivative, set it equal to 0, and solve. We're going to do something similar. We're going to take the derivative, which is 3x squared plus 1. But we're not going to set it equal to 0 because what we're looking for here is a number C that satisfies the mean value theorem. And hopefully I haven't pushed that all the way off, have I? Yeah. Sorry, I pushed it all the way down. But so the conclusion of the mean value theorem is not that we're not looking for some input that makes it equal to 0. We're looking for some input that makes it equal to the average rate of change. So we want to set it equal to f of 2 minus f of 0 over 2 minus 0 is 2. And so this is the x that we care about. So this is the value that is going to quote-unquote witness the promise of the mean value theorem, the existence of that C. So let's solve it. So on the left we clearly have 3x squared plus 1, and then we can figure out these numbers from the right. So plug in 2, that gives you 8, plus 2 is 10, minus 1 is 9. And if you plug in 0, you get minus 1, so this is going to be plus 1, because minus minus becomes plus. Divided by 2, so this is 5. Okay, now solve this equation. And what happens? You get x squared is equal to, maybe I'll leave this 3 here, becomes 4, right? I took 1 away from both sides, and now x squared is equal to 4/3. And finally, x is equal to plus or minus 2 over the square root of 3. Alright, so there's a plus here and a minus here, and remember that the C that we care about, the C from the mean value theorem, is in AB. So in this case, C is supposed to be n, the interval from 0 to 2. The negative one is clearly not, right? And then you could say, well, Hunter, how am I supposed to tell whether the positive one is in the interval or not when I'm not allowed to use a freaking calculator? The reason you know the positive one is in the interval is because the theorem tells you that there is one in the interval, right? So one of them has to be in there. One of them has to be in the interval from 0 to 2. That's what the theorem is promising. It's definitely not the negative one, so it must be the positive one. And so the answer is C equals positive 2 over the square root of 3. And that was kind of long, huh? But it's done.